Okay, so if there are no questions, I'll start. So last time we started discussing the motion of a point particle in the Schwarzschild metric. So let me just briefly recall what we had gotten. So we had gotten the relation between phi and rho. Okay, so d phi d rho was constant k. Okay, this is the equation we had gotten. And let me remind you that psi of rho is 1 over 1 minus 2 gm over rho. And psi of rho is 1 minus 2 gm over rho. And you had also gotten an equation, of course, for the time dependence. Okay, so if you are interested in finding the time dependence of phi, for example, d phi dt, that was given by k over rho square times psi of rho. Okay, so if you want to know how phi changes as a function of time, you can use this equation. And that in turn will also tell you how rho changes as a function of time by this equation. But for most purpose, we'll basically work with this equation over here. So the first we want to start, that problem that we want to study is bending of light. So let me explain what it means. Okay, so let's suppose that we have a point mass sitting here, okay, which you can take to be rho equal to 0. And let's suppose that there is a ray of light which is passing along nearby, okay, this point mass, which will follow a trajectory like this. Okay, so far away, of course, it just comes along a straight line because the metric is just flat. But near the point mass, it will bend. And so effectively, what is going to happen is that if you extend it, and if you extend this, there is some angle alpha by which it bends. So if we observe the star, it would appear as if it's at a different position in the sky than what it really is. Okay, because the light from the star is coming to the observer along a curved path. Okay, so the observer, if we didn't know about the existence of this massive object, then the observer will simply think that the star is coming, the light is coming from somewhere in this direction. Okay, and hence the apparent position of the star in the sky will change. So this angle alpha is what we want to calculate. And this angle alpha is also what is measured, what can be measured. I'll discuss later how it was actually measured. But this is what you want to calculate. Are there questions on this? Okay. So let me emphasize again, the idea is to try to follow the trajectory of light in the background of Schwarzschild metric.
For light, n is supposed to be 0, right?
Yes, indeed, n will be 0. Right? So n equal to 0 for that's what you are going to substitute. null geodesic. So the first thing is to try to determine this constant of integration. N is 0, right? But how do you determine k? And to determine k, we simply use the fact that d rho d phi equal to 0 at rho equal to rho naught. Okay, so what is rho naught? Rho naught is basically this point, okay, where the closest approach. So this is what we are calling rho naught. So this is the closest approach. So now you just substitute it here. Okay, n is 0 anyway. So you get k square over rho 0 square is 1 over psi of rho 0. Right? Because d rho d phi is the inverse of this. So the minus half becomes plus half. So this has to vanish. So k square over rho 0 square is 1 over psi 0, psi of rho 0. And this implies that k square is rho 0 square over psi of rho 0. Okay. So you are now going to rewrite this equation by substituting for n to be 0 and k square to be given by this. Is this clear? So let me write that equation. So d phi will be given by k over rho square. Okay, k we can substitute afterwards. This k is outside. Psi of rho d rho. And then we have 1 over psi of rho minus rho 0 square. Rho 0 square over rho square. Okay. So the idea now is that we have to integrate this. So let me write this in a slightly different way. Okay, then we'll make approximations. So this one, I'm going to take the 1 over psi of rho outside. That becomes psi of rho to the power half, right? Because the minus half here, and then you have 1 minus rho 0 square over rho square times psi of rho over psi of rho. Okay. Now let me explain the approximation that we are going to make. So the approximation that we are going to make is basically that this quantity 2 gm over rho, right? And in particular, in this case, it corresponds to 2 gm over rho 0 is much less than 1. And since rho 0 is the closest approach, this will also imply that 2 gm over rho is much less than 1. So this approximation basically follows from the fact that the Newton's constant is very small, typically. So just to give an example, that for the sun, 2 gm is roughly 3 kilometers, which is of course much smaller than the radius of the sun. Right? So it says if the sun had been a completely compact object, then this 2 GM would have been 3 kilometers. But essentially what it is saying is the kind of distances that are involved in. Suppose you are trying to find the bending of light that as it goes around the sun. Clearly the distance that the minimum distance that the light can have is much larger than the radius of the sun, right? Because light cannot simply enter the sun, then it will just get blocked. So typical ratios that you will be encountering, okay, in any practical situation is where this 2 GM over O0 is much smaller than 1, and that's the approximation I'm going to make. This of course precludes the case of say light scattering from black holes, okay, where for black holes the there's no star, there's no star, right? So you can in principle send a light very close to the horizon, okay? And there of course this approximation will not work, right? Then you have to do an exact calculation. But right now we are going to make this approximation because for ordinary stars, okay, this approximation is a valid approximation. So once we have this, right, we can basically expand psi in a power series, and we'll keep up to the first non-trivial order in GI. Is this clear? So then let's take this expression first, right? We'll take this expression first and make the approximation. Now, the other point I wanted to emphasize here is that you see xi and psi are opposite, are inverses of each other, right? So once you have pulled out this factor of psi of rho, okay, these two terms just cancel. This and these just cancels. So that's some simplification. Okay, so this term that I can write as 1 minus rho 0 square over rho square. Psi, if you recall, is 1 minus 2 GM over rho. So I can write this as 1 minus 2 GM over rho plus 2 GM over rho 0. Plus higher order terms that we are not giving. Right? That will involve the square of this ratio. So this, sorry, minus half. So this can be simplified a bit. So you get 1 minus rho 0 square over rho square, that's the leading term, plus rho 0 square over rho square times 2 GM times 1 over rho minus 1 over rho 0. So now we'll further take this 1 minus rho 0 square over rho square outside. So I write this is 1 minus rho 0 square over rho square to the power minus half. And then 1 plus rho 0 square over rho square times 2 GM. Okay. And you see here there's a 1 over rho minus 1 over rho 0, right? Which I can write. Okay, let me write the result anyway. Okay, let me write it in the next slide. I write this as times 1 plus, I'll just write this and then we'll see if we agree. Okay, so what I have done here is that I have just taken this part out, right? So there is a, so you have to divide by 1 minus rho 0 square over rho square, right? So which is basically rho square minus rho 0 square over rho square. But you see this one will also have a factor of rho minus rho 0. Okay. So I have just cancelled out that rho minus rho 0 factor that is common between here and here. Okay. And then the rest of the term basically takes this form, right? So once you have cancelled the 1 minus rho 0 over rho piece, there's a 1 plus rho 0 over rho piece that remains in the denominator, right? That gave rise to this rho plus rho 0. And then the rest you can just work out. Is this clear?
Can you please explain the algebra again?
Yeah. So there is a 1 minus rho 0 square over rho square. I am factoring out, right? Okay. So you have to divide this by 1 minus rho 0 square over rho square. 1 minus rho 0 square over a square, we can factor into 1 minus rho 0 over rho times 1 plus rho 0 over rho. This one, on the other hand, has a factor of 1 over rho minus 1 over rho 0. So that's proportional to 1 minus rho 0 over rho, right? So that factor I just cancel out. That's why instead of having in the denominator, instead of having 1 minus rho 0 square over rho square, we essentially get 1 plus rho 0 over rho, because that's the factor that remains. The other factor has cancelled out. So that is responsible for this rho plus rho. Is this clear? And the minus sign comes because here you see the factor is rho 0 minus rho. Here the factor will be rho minus rho 0, right? Because there's a rho square minus rho 0 square sitting here. Is this clear? And then the next step is to again expand this out, right? This is 2gm is small. Okay. So I can expand this out as 1. This minus of basically now multiplies this. Okay. So it cancels the 2, it cancels the minus sign. So you get 1 plus, you see here is rho 0 square. Something is, I think I made a mistake here. This is not rho 0 square, this is rho square. Yeah. So you get 1 plus rho 0 square over rho plus rho 0. Okay, so one factor of rho 0 gets cancelled. Rho square gets cancelled. Okay, there's a one factor of rho 0 in the numerator, one factor of rho in the denominator. And then this minus 2gm multiplied by minus half just gives you dHgm. Okay. Again, this is straightforward algebra, but you should be able to work this out. Right? So the important point is that you are doing an expansion in powers of 2gm over rho naught. Right? So higher powers of 2gm over rho naught, we are just ignoring. Okay. So you are basically now going to substitute this in this expression and see what we get. Oh, and this factor is also there. So I should have written this. Right? 1 minus rho 0 square over rho square to the power minus half. Okay, so this is the final expression that we get for that bracket, whatever is in the curly bracket is given here. Are there questions? So I'm going to now substitute this here.
I mean, shouldn't there be a minus sign? I mean, in the previous slide, this expression inside the bracket. I mean, there was a minus sign there, right?
this minus
Okay,
sign.
okay. Yeah,
And then
minus and
minus half.
minus. Okay, okay. I see.
Yeah. So it's like I'm using the factor 1 plus x to the minus half is 1 minus
Yes.
half x for small
Okay,
x.
okay.
Yeah, so that's why the minus sign went away. Okay, so at the end of this, we get d phi as k over rho square d rho. Okay, so here I have just done a little bit more manipulation, right? You see, there is a rho 0 over rho plus rho 0 times rho. I just wrote it as a difference between two terms. 1 over rho and 1 over rho minus rho plus rho 0. That's what I've written. So now the total change in phi, delta phi, I can calculate as follows. You see the ray of light comes from infinity, reaches rho 0, and then goes back from rho 0 to infinity, right? So look at this geometry over here. So to calculate how much is the change in phi as the ray of light goes like this, we can just calculate twice the change starting from rho 0 to infinity, because the trajectory, of course, is symmetric around this point of closest approach. So I'll integrate that equation, right, d phi d rho, from rho 0 to infinity, right, instead of from infinity to rho 0 and then back to infinity. I'll integrate it from rho 0 to infinity and just multiply it by 2. So then delta phi will be given by 2 times integral rho 0 to infinity k over rho square d rho. Is it clear? Because you have to just integrate it. Let me give the substitution. So we substitute rho equal to rho 0 sec u. Why sec? Because rho is always larger than rho 0, right? And the sec is a function that's always larger than 1. So u here will go from, so rho starts from rho 0. So u goes from 0 to pi by 2. Right? At u equal to pi by 2, this sec pi by 2 is 1 over cos pi by 2, that's infinite. So you can just take u from 0 to pi by 2. So with this, I can get right delta phi as 2 integral rho 0 to infinity k. Okay, k I have not substituted yet, but I can do it afterwards. So d rho, so the differential of sec is sec times tan. So rho 0 times sec u tan u over sec square u. Here you have 1 minus cos square, right? Minus half. Yeah, because rho 0 over rho is 1 over sec, that's cos. Okay. And then here you get 1 plus gm times 1 over rho. So gm over rho naught, let me take this out. 1 over rho is 1 over sec, that's cos, minus 1 over rho plus rho naught, that's you can check is cos u over 1 plus cos u. Okay, you just have to substitute rho equal to rho naught times sec u, and then write sec as 1 over cos.
I think there should be a rho naught square next to sec square u also.
Yes, thank you. So this one I write, so 2k over rho naught. Okay, let's now try to see if we can substitute for k. So k was somewhere. So k was rho 0 over psi of square root of psi of rho 0, right? So we're going to make that substitution. So this is rho 0 over square root of psi of rho 0, okay, 2. And then there is a 1 over rho 0 from here. Okay, so that rho 0s cancel. And now you have integral rho 0 to, sorry, this is not rho 0. In terms of u, it's from 0 to pi by 2. So this is from 0 to pi by 2. This is 1 over sine. So basically, you can check that 1 over sine, when you combine with this, everything cancels. So you just get du times 1 plus gm over rho naught cos u. And then this other term minus gm over rho naught. I'm going to write cos u as 1 plus 2 cos square u. So 1 plus 2 cos square u by 2. Sorry, 2 cos square u by 2 minus 1. Cos u is 2 cos square u by 2 minus 1 over 2 cos square u. Okay. So this becomes this part. Let's try to simplify a bit. So this becomes 1 plus gm over rho 0 cos u minus one part is 2 cos square u, gives you just cancels, so minus gm over rho 0. And the second one is plus gm over 2 rho 0 times x square u by 2. Right? Now all the integrals are elementary, right? Because this gives you pi by 2, the u integral. This gives you gm over rho 0 times sine u, right? Sine u at pi by 2 is 1. So this just gives you gm over rho 0. This gives you minus gm over rho 0 times pi by 2. And this one, sec square u by 2, half sec square u by 2, when you integrate, you just get tan of u by 2, right? D of tan u by 2 is half sec square u by 2. So you just get tan of u by 2 between 0 and pi by 2, right? So that basically picks up tan of pi by 4, which is 1. So this then gives you 2, the 1 over square root of psi rho 0. I'm going to write as 1 plus gm over rho 0. And here I get 1 plus, sorry, not 1, pi by 2 plus gm over rho 0 minus gm over rho 0 times pi by 2 pi by 2. And then this one is just gm over rho 0, right? Because this, when you integrate, you get tan of u by 2 plus gm over rho 0. Okay, so I'm going to write in the next page in a liter form. So you get two factors of gm over rho 0. You see 2 gm over rho 0, sum of these two. And then we have pi by 2 times 1 minus gm over rho 0. Okay, so let me write that out. So delta phi is 2 1 plus gm over rho 0 times pi by 2 1 minus gm over rho 0 plus 2 gm over rho 0. Okay, this is what you get from this expression over here. And now I'm going to multiply it out, okay, and ignore terms of order gm over rho 0 squared. So when you multiply this out, you get pi times 1 plus gm over rho 0 times 1 minus gm over rho 0, right? That's 1 plus higher order in g square m square over rho 0 square. So that we ignore. So this product just gives you pi. And the second one, right, you can ignore this gm over rho 0 because that will again give you g square m square over rho 0 square. So we get plus 4 gm over rho 0. Is this clear?
Did you use any expansion for 1 by root psi of rho 0?
Yes, I did here.
Okay. Okay.
Right, 1 over root psi of rho 0, I wrote it as 1. So this is 1 over square root of 1 minus 2 gm over rho 0.
Okay.
Right, that I wrote as 1 plus gm over rho 0.
Okay, fine.
So now here you see that this pi is a trivial factor. That's just the forward scattering, right? If you had a star over here, and if a light ray passed just straight, then when you extend it, right, the change in phi, right, and then when you go to the polar coordinate, the change in phi would have been pi, right? Because this change in the limit when this goes to minus infinity and this goes to plus infinity, this angle would have been pi. So the pi is just forward scattering without bending. So this is the term that is extra, right? So this represents this one represents the effect of bending of light. Okay. So because of this effect, the apparent position of, say, a star, right, whose light is you are observing, will get shifted by an angle of 4 gm over rho 0. Right? That's what it means. Okay. So shift in the apparent position. So suppose, okay, let me draw this picture again here. Right? Let's suppose that there is a star here. Well, let's call it sun. Right? That's how it was observed in the first place. So suppose this is the sun, and this is some star. Distant star whose light we are seeing. This is us. And then the light ray from the star comes, bends, and reaches us. Okay. And what we see is that if we draw the tangent, okay, this is the apparent direction from which the light will be coming. On the other hand, if the sun was not there, then the light will just come from there, come straight, without bending. So this angle is this 4 gm over rho 0. Is this clear? So this is the implication that if we are observing light from a star, from a distant star, right? And if there is nothing else on the path, along the path, right? Sun is just one object. Right? Assume there is nothing else on the path, along the path, then we will see some position of the star in the sky. Now, if it so happens that the sun, there is a, if you put some massive object along the path, like the sun, then the apparent position of the star will shift. Okay, and the amount by which it will shift is this 4 gm over rho 0. Are there questions?
So in the Newtonian case, delta phi would have just been pi, nothing else.
See, in the Newtonian case, we don't even know how to calculate because Newton doesn't tell us how gravity acts on light, right? If you assume that, yes, gravity doesn't act on light, right? Photons are massless object, right? And if gravity couples to mass, then it shouldn't couple to light. Then the answer would have been just pi because the photon would have just gone straight.
How do we estimate R rho 0? I mean, because it doesn't seem.
I'll tell you how to estimate rho 0, right? So let me now describe the experiment that was measured, that was used.
Can I just one more explain that pi factor?
The pi factor? Oh, pi factor is that if we just go, suppose there is no scattering, right? It just goes straight. Then the change in phi, right? Well, look at the azimuthal angle measured from here, right? The azimuthal angle will be the angle that this line makes, right? As it goes to infinity. And as it goes towards infinity, the azimuthal angle that will be made is this line. So this angle in that case would be pi, right? Imagine that you are sitting here. We have some object coming from infinity along in one direction and going off to infinity along another in the opposite direction. Right? Then it will, the azimuthal angle will change by pi. That is this factor of pi.
Okay, fine.
Right? So this is the extra effect that happens because of the bending of light. Right? If light didn't bend, you should get the answer pi. Right? And that's what we are saying here.
Okay, got it.
Okay. Any other question?
So, could you quickly explain why the integration was given from minus infinity to infinity to rho naught to infinity, twice of rho naught to infinity?
Oh, because I'm using the fact that the motion is symmetric around this line, right? This is the line at which this is the distance of closest approach, right? So I just calculate the change in the angle in this part of the path and multiplied by 2. Right?
So saying that
add the same integral twice.
I see. So it's like saying that the star is directly behind the sun.
Star is directly
behind the sun on the line of sight.
Yeah,
or...
exactly. Yeah. Okay. I mean, yeah. If the star was not directly behind the sun, right, then I mean the amount of bending will be very small, right? So for all practical purposes, you can think of the star as being just directly behind the sun. But it doesn't even have to be directly behind the sun. Let's look at this way. Let me consider. Okay, it doesn't have to be directly behind the sun. By the time you have gone to infinity, it will be as if you are directly behind the sun. Right? Imagine that the sun is here, right? And the star is somewhere there, but far away. Let's draw the perpendicular distance, right? As the star goes to infinity, right, this angle becomes pi by 2, right? This angle becomes pi by 2. Is that
yes.
Yeah? Right? Because the star is really at infinity. I mean, if you are thinking of the star being very far away, right? Similarly, we are thinking of us, the observer, as being very far away, right? So this angle would also have been pi by 2.
Yeah.
Right. So because of these large distances, it's as if the star is directly behind the sun, right? But it doesn't have to be directly behind the sun. Because you are really thinking of the light coming from infinity and going up to infinity.
I see. So any apparent changes in that, the delta of delta phi would be very small. That's what you were saying.
This, yeah, I mean, if the star was not at infinity, then there'll be some small number.
Okay.
It will not be pi by 2, but differ from pi by 2 a very small amount. But that distance is really small. That quantity is really small.
Okay.
Right?
Thank
Because
you.
you are thinking in terms of the ray. So this is the solar system size, right? Whereas the star is much farther away.
Yeah, got it. Yeah.
I mean, one more question.
Yes.
If there is a situation in which, let's say, either the source of light or the of the observer, either if one of them is, let's say, at a finite distance away from the object, the sun, the massive object, let's say,
Yes. Yes.
yeah, if one of them is not far away, how would we
Yeah.
proceed with
Then
the
you have to make
calculation?
for the correction, right? You don't integrate all the way to infinity.
Okay, and then this twice thing won't work, right?
Exactly. Yeah. Right. But for the kind of thing that you are interested in, right? Both
Yes.
the star as well as the Earth, we can think of as being very far away, almost at infinity, right? So basically, what is important is the ratio of this to the distance of the star and the Earth should be small, right? The distance of
Okay.
closest approach to
Yeah.
what is it, and that is
So
indeed.
if we were to, let's if we think of the mass of the m here as the solar mass.
Yes.
So would the sun, the distance of the Earth from the sun, would that be, big enough for us to have for this kind of an approximation to be?
Yeah, that is big enough because
Valid.
rho zero has to be. You see that this it depends on this 2 gm over rho zero, right?
Yes. So
2 gm is 3 kilometers
for a solar mass.
for a solar mass.
Okay.
So for this effect to be appreciable, right?
Mhm.
Rho zero cannot be too big anyway, right?
Yeah.
Maybe few thousand kilometers.
Okay.
Few thousand kilometers will give you 1/1000, right?
Yes.
Make it a little more maybe, but that's much smaller than the Earth Sun distance. Right, so that's what we are exploiting. Yeah, so this ratio will take to be almost zero, right? This rho zero over the Earth Sun distance. This is the effect that you are observing.
Okay.
But if it's not true, right? If you are observing from somewhere closer, we basically have to make for the corrections, right?
Okay.
So this integral can be done to any right? You don't have to do the integral all the way to infinity.
Okay.
Okay.
And
So
can you explain
yes.
how did you identify the 4 gm by rho zero to be that angle which is measured from Earth?
This one?
Yeah, how did you identify that as the 4 gm by rho zero?
Well, this is the answer we got, right? And I'm saying now that if this light had traveled straight without any bending, then this would have been just pi, right?
Yeah.
The angle.
Mm.
So the excess is what is the effect of bending,
Okay. Mm.
right? So that's that's what you identify as a result of as the effect of bending, right? If there's no bending, then you'll just get the answer pi. If it had gone straight.
Okay. Okay.
Shouldn't
Fine.
it be 2 gm by rho zero because the net bending is 4 gm by rho zero.
Yes.
So this angle you have marked in this diagram, this should be 2 gm by rho zero, right?
No, this is not 2 gm by rho zero. Because this is the angle. Okay, let me Because if the sun was not there, right,
Okay.
then the starlight would have come straight.
Yeah.
Okay. If the presence of the sun bends the light, right?
Yes.
So I think the confusion is that we are thinking of this being as a finite position, but these distances are really large, right? If you think of this as
Okay,
a
okay.
parallel rays coming, the position of the Earth really doesn't make a difference.
No, the thing is, I mean, when light ray left the star,
Yes,
it would have gone in a straight line, right?
yes. It would have
The
gone in a
net-
straight line and come to us.
And then this 4gm by rho 0, this is the net bending of the light ray. So this light ray, the net bending of this light ray is 4gm by rho 0.
Exactly.
And this angle you have marked, it is half the bending of the light, right? Isn't it?
No, okay. It looks like half the bending of the light. I think that's because of the distances. Let me just
Okay, okay.
right.
Yeah.
Let me just that. So the picture is the following, right? That there is a ray of light coming like this. Here is the sun. And this, think of this as a parallel ray of light. Coming like this. This is the sun. And the result is that as a result, this parallel ray of light is bending. Okay. This, how much is the bending? This net bending is 4gm over R0, right? 4gm over O0. This part you agree?
Yeah.
So it's the angle between the initial parallel ray that was coming and the final parallel ray that is going out.
Yeah.
And the Earth happens to be somewhere here. We observe the light from the Earth. So from the Earth, it will now look like the star is situated at an angle like this. Whereas earlier, the Earth was receiving parallel rays from the star like this. Is this clear?
Yes.
Yeah. So that you have to think of it's a parallel beam coming from the star, right?
Okay.
Not that because the star is so far away that it's as if it's a parallel beam. And that whole parallel beam is getting bent and coming to us. And you are comparing what would have happened if the sun was not there, in which case the parallel beam would have come in one direction. And in the presence of the sun, the whole parallel beam has gotten bent, and now it's coming from a different direction. Is this geometry clear?
Yes.
Any other question? Okay, so let me now then describe how exactly it is measured. The actual experiment. So basically, let's suppose you have a star. We have a star on the celestial sphere. So its position on the celestial sphere is fixed, right? Because the stars don't really move on the celestial sphere. Okay, Earth of course moves, right? So the celestial sphere rotates, but that we know how to correct, right? I mean, astronomy is reasonably well understood, so that the fact that the celestial sphere actually moves from the Earth's viewpoint, that you know how to correct. Okay? So the star has a fixed position on the celestial sphere, right? Say related to the other stars.
Oh, what is this celestial sphere?
What you see in the sky.
Oh, okay.
In the sky, that every star has a relative position with respect to the other stars. and that doesn't change.
Okay, okay.
Right? The whole sky looks like it's rotating. That's because Earth rotates. Okay. But that we can correct for. So you just think of, so celestial sphere is the, basically tells us the star map in the sky.
Okay, okay, okay.
And so the, if you have a star, we can locate it on the celestial sphere at a fixed angle related to other stars.
Okay, okay.
So now suppose, okay, that this is the star. This is us. And some object like the sun comes on the way. Other stars cannot really come on the way because the star, all the other stars are fixed in the sky, right? The sun can come on the way because sun is close enough to us, okay? So that as we are moving, right, sometimes the sun can come on the way between us and the distant star. If it happens, okay, if the sun comes on the way, then this light will bend. Okay, this light will bend. So this whole parallel beam is going to get bent. Okay. And when we receive that light, okay, I mean, again, you think about somewhere here. When we receive that parallel light, okay, it will look like as if it's coming from a different angle. Right? So it's as if the position of the star has moved on the celestial sphere. Is this clear? So that's what we need to observe.
What is this angle value in like 4 GM by rho naught?
What is the angle value?
For 4 GM by rho naught.
Yeah, what is the, okay, that depends on rho zero, right?
Yeah. So it's order of magnitude.
Yeah, it's typically very small. I don't now remember the exact order of magnitude of the first observation, but it is typically quite small, right? Because it's like 3 kilometers and rho zero certainly is larger than the radius of the sun, right? So the point is that we can measure this rho zero. How can we measure rho zero? Because we know the position of the sun very well, right? I mean, again, astronomy tells us that if it so happens that the sun comes in front of the star at a given time, right? Imagine that we fix a time, at certain time we know that sun has come in front of the star. Okay? Then how much is the distance from the direct path? This is the star. How much is the distance from the direct path? This is Earth. This is sun. This distance, which is rho zero, is known. At any given time. Okay, this is just from astronomy. Okay. So if we could make this observation, right, at a given time, suppose that for some fixed time, we find that we find how much the star has moved in the sky. Okay? And at that time, we also know how much would have been the distance between the path of light and the sun. Okay? We could figure out, I mean, we could compare the observation with the experiment, right? We can calculate the deflection angle to be 4 GM over rho zero, okay? And we could make that observation. Now, the problem, of course, is that when the sun is in front, right? I mean, in this geometry, okay, we cannot really see the star, right? Because the sunlight will basically block the view of the star. So the experiment that was performed was during the eclipse, right? That this kind of observation you can only do, right, when there's an eclipse. So when there's an eclipse, we can see the star. And measure its apparent position. its apparent position. Okay. So because of this, we don't really have a choice of when you observe, right? We have to observe during the eclipse, and you have to hope that there is a star behind the sun, okay, or closely behind the sun at that time. So this is what was observed. And then of course, rho zero is basically the distance that the light, that the sun is from the path of the light at that time, at the time of the eclipse. So this is what is compared, right? We measured this angle at the time of an eclipse, how much the apparent position of the star has changed in the sky, and we compare this with 4 GM over rho zero. Is this clear?
So initially we made one measurement when it was not just behind the sun, and we got
Yes.
one value. Then we again measured during eclipse, because then
Exactly.
only we can see the star, and we
Exactly.
compared this value. Okay.
That's right. So that's the experiment, that you know the position of the star with respect to the other stars when there is no sun along the path. That is a true position. And then you measure it again when the sun is present, right? How much, what angle it makes with respect to the other stars. And this difference will be 4 GM over rho zero.
So this angle that we have here, so it's the displacement of the position of the star from its expected position, I mean, in the celestial sphere, right?
Exactly, that's right.
Okay.
Okay, so that's what we observe, this 4 GM over, and that's what you should compare with 4 GM over rho zero.
Yeah, but all these calculations are under the assumption that the mass distribution that we set for the sun was something spherically symmetric, right? So if it was not spherically symmetric, would we expect the expression for the apparent position to be, I mean, very different from this? I mean,
Yeah, it will, in general, it will not be, right?
yes.
Except that, I mean, it depends on rho zero, right? Suppose rho zero is larger than the radius of the sun, much larger, right?
Yes.
Then the sun can be thought of as a point object.
Okay, then spherical symmetry holds.
Yeah, then effectively spherical symmetry holds.
Okay. Yeah.
Yeah, but otherwise, meaning sun is roughly spherically symmetric, right? So I don't think that is that is an issue.
Yeah. So that if the, I mean, the distance of closest approach is large enough, I mean, this kind of calculation will always hold.
Exactly. Right. And the point is, this is the leading term, right? Then of course you can always make various corrections, right? Correction from deviation of spherical symmetry, maybe higher order corrections that you have ignored, the g square m square over rho zero square terms. Right? All of those corrections can be made. This is just the leading term in that expansion. So this is one of the classic tests of Einstein's theory, right? The first one was the redshift, I already mentioned, right? This is a classic test. And then the third one is what I'm going to describe next. And that is the motion of the planets, right? How does Einstein's theory differ from Newtonian gravity as far as the motion of the planets is concerned? But are there any further questions on this?
Yeah, so we measure this apparent position during eclipse when light is being bent by the sun, and we also measure its position in the celestial sphere when sun is not around. Then we have this, so we have that value, but to compare it with 4 GM by rho zero, we need to have measurement of rho zero separately, right?
Yeah, but that's what I was saying. The rho zero is measured because the position of the star and the sun in the sky are very well understood, right, from astronomy.
Oh, okay. Yeah, okay.
So we know what would have been the path of light and how much sun would have been away from that path.
Okay.
This is just from astronomy that we can predict what this rho zero is, right?
Yeah.
You don't really need any separate measurement.
Okay.
Also, the data from astronomy could already be less, say some other mass distribution is there which we are not like aware of. So are there certain arguments which like say take a random mass distribution and still show this effect?
See, basically what happens is that the stars are, I mean, you really typically don't have a star eclipsing another star, right? That distance is typically very, very large. I mean, even if the angular scale is small, right? The actual physical distance of the line of sight, right? Imagine that you are very far, right? And there's another star here, right? Which is at a very small angle. But actual physical distance between the line of sight and the star will be very large, right? Because it's very far away. So you don't worry about other kinds of mass distribution.
So it's a very isolated system,
Exactly.
sort of.
Right? The very fact that we are seeing a starlight means it's isolated in the sky. There is no other further mass distribution along the way. Right? And the point is, if there's a fixed mass distribution, right? It doesn't really matter, because that's not going to change, right? It's the change that we can observe. Imagine that there is another star nearby, right? So that there is a bending, but that bending will remain constant, right? Because the stars don't move relative to each other very much in the sky. It's the sun that moves in that is apparent motion in the sky because of our motion, the Earth's motion, right? And that's how we can detect the change.
Measuring the change does the job here.
Pardon?
Measuring the change satisfies what we are trying to do here.
Exactly. Yeah. Right. I mean, imagine that there is some other fixed mass distribution which also causes a bending, right? But that's a fixed bending which is there when whether the sun is there on the path or not. Right? That will just cancel out in this inference.
Sir,
Yes.
so sun is not fixed in celestial sphere, right?
Sun is not fixed in celestial sphere, indeed.
So such an experiment will require, I mean, taking measurements different times in the year, yeah, or
Well, see, different
when
times.
Earth changes the position.
If you could take many measurements at different times, right, you could get many data points. The problem is that we can only measure the position of the star when it's behind the sun, right, or when it's almost behind the sun during an eclipse. Right, because otherwise the light from the sun will totally obscure the position of the star, right?
Yeah.
So that's why we make just two observations. One in the night when there's no sun.
Okay.
Then you can find a position of the star in the celestial sphere. Right? And then once during eclipse, when the sun is in front of the star.
But if star is behind the sun and we take a measurement in night, the star won't be visible, right? And star will be below the horizon, like sun.
The star is below the horizon.
Like sun is, I mean, because if it is behind.
At night you observe the stars that you can observe in the sky. Right?
Yeah.
At that time, indeed, the sun is somewhere else, right? But the position of the sun in the celestial sphere keeps changing.
Yeah.
Right?
Okay.
So at some point, the sun may actually come in front of the star.
Okay.
Right? That is the time we want to observe. But when the sun comes in front of the star, right, we cannot observe the star, right? So that's why you need eclipse.
Yeah.
So this is important, that this kind of experiment can only be done because the position of the sun on the celestial sphere keeps moving. Right? In different times of the year, the sun is in different position in the celestial sphere.
Yeah.
So you have to wait till the sun comes in front of the star, right? And it eclipses it. Or the sun gets eclipsed, right? The star is almost behind the sun. Okay? Then you can change this apparent position and then compare it with what we expect it to be on the celestial sphere.
Yeah. Okay.
Any other question?
So as rho 0 goes to 0, for example, tending to 0, so this angle delta phi goes large.
But see,
Is it
this expression has been derived assuming that 4 GM over rho 0 is small. Right? We cannot really trust this when 4 GM over rho 0 is large.
okay?
Then you have to do the full calculation, right? You can't make this approximation anymore.
Right.
But what you can say is that, yeah, smaller rho 0 is, the larger this number is, right? But it is trustable only when the number remains small.
So you mean the corrections, the additional corrections which should be there because of the smallness of rho 0 would tend to make this delta phi smaller.
No, I'm not
As-
saying it will make this delta phi smaller than what it would have been otherwise. Right? I mean, it's not, one shouldn't say small or large, right? This formula will not be valid anymore, right? Let me put it this way. That you have to actually redo the calculation exactly, right? Without making expansions of this kind.
Okay. But I think I was expecting that the leading order would still be this thing, right?
Well, see, when this is of order 1, right? What would I mean by leading order? It is certainly true that if rho 0 decreases, right? Suppose rho 0 is large, but it becomes a little smaller, then this angle will increase.
Right.
That certainly is true. But when this number becomes of order 1, right, then you cannot trust this formula. Right? Because we expanded and we ignored all the higher order terms, right? In this analysis. So all those now have to be taken into account. Right? It is certainly possible because after all, it's just a differential equation, right? If you look at the starting point, right? In principle, you can do an exact calculation, right? Just integrate this exactly, maybe put it on a computer and try to integrate this, right? Even for small rows. But it's just that formula is not valid.
I see. Thank you.
I have doubt in this rho 0 measurement.
Yes.
So how did exactly they measure this rho 0? Because rho 0 is the at what distance the light is with respect to the sun, which is measured by the observer on Earth, right?
Yes.
Okay, so this is basically we know the distance between sun and Earth, and the observer will observe the angle at which the light is coming to them.
Yes, but the point is, much more than the distance between the sun and the Earth. We know the position of the sun on the celestial sphere at any point in time, right?
Okay.
That's standard astronomy. So we know exactly which position at the time of eclipse, right? When you're observing it, we know exactly which position the sun would have been on the sky, right? And we know what path the light would have followed because we know the position of the star on the celestial sphere.
Okay, so using some previous knowledge in astronomy, we have a pretty good idea about rho 0.
Exactly.
Okay. Okay.
Right? It is not something that you do measure during that experiment, right? You just use your prior knowledge of astronomy to figure out what rho 0 would have been at the time of eclipse.
Okay, fine. And is the rho 0 is necessary to be the closest approach, right? Because in the derivation we assume to be the closest.
Exactly, it's the closest approach, right? So in this geometry, right, you think of the rho 0 as a perpendicular distance, right? Roughly. I mean, of course, the metric is not exactly a flat metric, right? But that intuition is good enough for us. Right? It's a perpendicular distance of the sun from the light path that the light will follow.
Okay, got it.
Okay, so let me then start with the next one, right? And I'll We'll probably complete it only next time. So what you want to do next, to study next, is the bound orbits. So let me write the equation again, write the same equation, but this time n is not 0. So if the orbit is bound, right, that means rho takes value in a finite range, right? That can be some minimum distance, some maximum distance. So you expect that the plot of rho versus phi, will be some oscillatory function like this. So this one I'll call rho plus, this is rho plus, and this is rho minus. So as phi increases, rho oscillates. Now, when I say as phi increases, let me also write the other equation, d phi dt was given by k over rho square times psi rho, right? K over rho square times psi rho. So you see that if k not equal to 0, then d phi dt is never 0. If d phi dt is not 0, is never 0, then it cannot change sign, right? Because in order for it to change sign, d phi dt has to go through 0. So this means that phi is either monotone increasing or monotone decreasing function of time. So phi keeps changing in the same direction, right? And that's for definiteness, assume that phi keeps increasing. Okay. But rho keeps varying, right? Rho is bounded, right? So it oscillates between some maximum and minimum value. And this is the motion that you have to study. Now, in particular, the quantity of interest for us will be this difference. Let me call it change delta phi. So this is the change in phi between two successive peaks, two successive maxima. Or minimum is the same. Now, why is this important? This is important because if we want the orbit to be periodic, then we want that when rho comes back to its original value, right? So suppose you start from here and it comes back to the same value. We want the phi in that case to change by a multiple of 2 pi, right? That if delta phi is 2 pi n, for integer n, then the orbit is periodic. Otherwise, it is not, because when rho comes back to its original value, right, the phi, the angular position, gets shifted, right? Because phi and phi plus 2 pi are the same points, but phi and phi plus something else, right, which is not a multiple of 2 pi, doesn't represent the same point in space. So a periodic orbit requires that delta phi should be a multiple of 2 pi. And indeed, this is what happens in Newtonian gravity. Right? The orbits are periodic, and that's because delta phi turns out to be a multiple of 2 pi. But we'll see that this is no longer going to be the case in Einstein's gravity. Right? So our main task is to calculate this delta phi. Right? How much does phi change between two successive peaks? Is this question clear?
Can you repeat what you said, like what we'll see in the Newtonian case?
That in the Newtonian case, delta phi will turn out to be a multiple of 2 pi. In fact, it's exactly 2 pi. So because of this, right, this point and this point represents exactly the same point in space, right? Because rho values are the same and the phi values also differ by 2 pi. But if this delta phi is something other than 2 pi, right, then basically maybe I can describe the motion, right? What's going to happen if delta phi, suppose delta phi is not equal to 2 pi, then what's going to happen is that the orbit will look like this. The center, of course, is the same.
Is this happening in the same plane, or is it like a helix?
Same plane, same plane. It's a planar motion, right? Because you have seen that the equatorial plane, it doesn't leave the equatorial plane. So theta equal to pi by 2, right? So what's happening is that it's going almost like an ellipse, right? But the ellipse gets turned every time. Is this clear? Just imagine that this was the ellipse, right? Suppose in the Newtonian case, this is the ellipse. But this ellipse requires that when rho comes back to, suppose, okay, so this is the sun, right? This is the minimum, right? This is the place where the rho is rho minus. So if it has to come back to the same point, right, then that means that rho has to come back to rho, that rho minus, rho goes to rho, that as rho varies from rho minus to rho minus, right? Say it was at rho minus here, it went along once and it came back to rho minus. But in that process, then phi has to change from phi naught to phi naught plus 2 pi. Right? Because it came back by changing by 2 pi angle, right? This would have been a periodic orbit. But suppose when rho comes back to rho minus, right? Phi has come back not here, but somewhere here. Then the motion will be something like this, right? And then by the time phi goes to 2 pi, right, rho has already turned back. So it's as if the orbit will start precessing, right? The orbit is not fixed, orbit is rotating. As you make more and more orbits, the orbit keeps getting turned. That is the situation when delta phi is not a multiple of 2 pi. So this is the important point, the thing that you have to determine, whether delta phi is multiple of 2 pi or not. In Newtonian case, from our experience or whatever you have solved in the central force, right, we know that delta phi is 2 pi, right, because the orbits are periodic, are ellipses.
Yeah, I mean, it seems that it's not necessary for it to be 2 pi n, right? 2 pi times some rational number would do, right? Or some fraction.
Well, 2 pi times some rational number will not really do, because that basically says that yeah, it may become ultimately periodic, but
Yes.
one period will involve many more ellipses,
Okay.
right?
Yeah, but that would also be periodic, right?
Yeah,
In
it
some
will be
sense.
periodic, true, right? But it will require many more revolutions, right? It will not be the kind of periodic orbit you are familiar with in Newtonian gravity,
Okay.
right? Whether it's a simple that it's not that rho minimum is reached at any just one point on the orbit, right?
Yes.
In Newtonian physics. If it
Yes.
is not 2 pi n, then rho minimum will be reached at very different points in the orbit, right? That you can see from the previous picture, right? Rho minimum is here, right? Here rho becomes minimum here. But if these points don't have phi differing by 2 pi, then that means these are actually different points in space. So the minimum is reached at different points in space, which is not the case of an elliptical orbit. Is this clear? So let me say it again. So the goal is to calculate delta phi. By integrating the equation from one minimum to another, to the next. Or we can just calculate the part of the orbit between the minimum and the maximum, and then just multiply by 2. Okay, because it's really a symmetric orbit. So we can write, so delta phi that you want to calculate will be twice integral rho minus to rho plus k square root of 0 over rho square d rho, and then n minus k square over rho square plus 1 over sin rho. Right? This is what you'll calculate, and we want to ask, is this 2 pi n for some integer n? And again, we will see that in the Newtonian limit, indeed, it's 2 pi, but the correction due to general relativity makes it not an integer multiple of 2 pi.
In the above part, you showed d phi by dt is not equal to 0. That's simply to say that the planet will constantly keep moving in the same direction.
Exactly. Phi will keep moving in the same direction.
Okay.
Yes.
Okay.
Right? So phi, suppose it keeps increasing, right? That basically means that around the origin, it keeps revolving only in one direction. But the question that you're interested in is whether the change in phi is over one period of rho, right? When rho comes between, say, one minimum and the next minimum, whether that change in phi is a multiple of 2 pi. Right? Because if it's a multiple of 2 pi, right? Suppose the phi here and the phi here are differ by 2 pi, then that means in actual physical space, this point and this point represents the same point. Right? Because difference in 2 pi and phi is not a real difference in terms of physical space. But if this differs, if it is not 2 pi, Then in physical space, this point and this point are not the same.
Okay. And here we took the space from rho minus to rho plus and rho plus to rho minus to be the same to get that 2 factor.
Exactly. Yeah. Whether the differential equation is really symmetric, you can check.
Okay. Okay.
That whether you integrate from rho minus to rho plus or rho plus to rho minus doesn't really make a difference.
Okay, fine.
Okay, so let me just say how the integration constants are determined, and then maybe actually do the integral tomorrow. So determination of n and k. And here we basically use the fact that d rho d phi is 0 at rho equal to rho plus and rho minus. Right? Because this is where rho reaches its maximum value, and this is where rho reaches its minimum value. So this basically tells us that n minus k square over rho plus square plus 1 over psi rho plus is 0, and n minus k square over rho minus square plus 1 over psi rho minus is 0. Okay. And this you can easily solve, right? 2 equations in 2 unknowns, n and k square. So we get k square as 1 over rho minus square minus 1 over rho plus square inverse. Okay, so basically to calculate k square, all you have to do is just subtract the 2 equations, right? So the n drops out, and then that gives k square. To get n, we multiply this by rho plus square, multiply this by rho minus square, and then subtract, so that k square now drops out. So n is minus rho minus square minus rho plus square inverse, and then rho minus square over psi rho minus rho plus square over psi rho plus. So what we'll do next time is that we'll substitute these values of n square and k in the differential equation in this integral, and that's the integrate, right? And again, we'll use the fact, we'll use the approximation. We substitute and integrate using the approximation the 2gm over rho minus, right? That's the maximum. The rho minus is the minimum value of rho, right? The 2gm over rho minus is much smaller than 1. And then this is again a valid approximation. For example, for planetary motions, right? As we saw, 2gm is like 3 kilometers, right? And certainly the closest distance the planet goes to the sun is much larger than 3 kilometers. Right? So it's a valid approximation to use. And using this approximation, we will now calculate, we'll try to use this approximation in the previous integral and carry out the integral. But this I think I'll do tomorrow, next time. Okay, are there questions?
Will we have an offline class next week?
Yeah, I think next week you should have an offline class. Hopefully, yeah. Okay, any other question? Okay, so if not, I'll stop here and we'll continue next time.